Okay, so today our speaker is Boris Bilich, and he will tell us about non-commutative analytic geometry and spectral theory for the group D infinity. Please.
Thank you. Hello, everyone. So let me start. I just want to show my screen of my tablet. So I will talk about an infinite dihedral group and its Bannock representations. And I will construct the notion of spectrum of those representations. So let us start. Can you see my screen right now?
Yeah.
Yes.
Okay, so if everything is just fine, let's start. So the infinite dihedral group, the talk is spectral theory for infinite dihedral group. And this group is defined as a semi-direct product of the group with two elements and the infinite cyclic group, the group of numbers, the integral numbers, the group of integers, and the action of the group of two elements on this abelian group is the only non-trivial action. So it takes the generator to the opposite. So by generators and relations, this group can be described as A, B with A squared and AB equals 1. So that means particularly that ABA is the same as ABA minus 1 is B minus 1. And so B is the generator of the infinite cyclic group, and A is the generator of the group with two elements. And I will fix this notation for the whole talk. So A will always be element an involution, and B is an element of this cyclic group. But this group also has another useful presentation, and from these two presentations, we can study a lot about this group. So the second presentation is this is the free product of two finite groups with two elements, and these two, the equivalence of these two presentations is easy because we let elements of the first of the first group be A, and it's already an involution, and we can observe also that AB is also an involution, and there are no other relations between A and AB. So it's I also fixed the notation for this presentation to not mess with them, like X, Y, and X squared equals Y squared equals 1. And the isomorphism is X goes to A and Y goes to AB. And these two presentations of the groups are both useful, and they tell us much about the representation theory of the group. So the representations of this group are precisely two independent involutions in in my talk. It would be Bannock representations, but in every space, representation in every linear space is just an ordered pair of independent involutions. And this group, the first presentations presentation also tells us that this group is actually not far from a abelian group. So it has an abelian group of index 2, and this and this is helpful for constructing non-commutative geometry, because generally, for examples in non-commutative geometry, one usually seeks for some algebras and groups which are not far from abelian. And let me say a few things about a group algebra itself. So yeah, and about the group algebra of this group, I will work on over the complex numbers only. So the group algebra is obviously generated by two elements A and B, and the group algebra is has a matrix presentation, and the presentation is this. So it can be described as a matrix subalgebra of some some matrix algebra over some another algebra. So A goes to the regular involution, and B goes to this matrix with polynomial.
Excuse me, what do you call an involution? I mean, you said regular involution.
Involution is the element which is inverse of itself.
So it's an element of order 2.
Yes, it's an element of order 2. And so this is a matrix presentation of this algebra, and it will be helpful for us later. So
what's Z?
It's like a variable. So it can be embedded in the matrix algebra over one moment. It can be embedded in matrix algebra over over the algebra of polynomials.
As a subalgebra generated by A and B, which you just wrote.
Yes. So A goes to this this matrix, and B goes to this matrix.
Can Z be arbitrary?
It's a variable. It's like it's so this matrix is an element of matrix algebra over polynomial ring.
Okay, I get it. Sorry.
And then we can specialize and to substitute Z with some complex number, and we then receive a complex representation of the group. But it will come later. But also this group, although this group is quite close to abelian group, it has trivial center. So center of this group is trivial. but central of the group algebra is not trivial, and it is generated by one element. And I will denote this element also Z, and I will explain a bit later why. So it's generated by element Z, where oh my God, where Z is B plus B minus 1, B inversed, multiplied by half. So it is easy to check that this element is central, and it is a bit harder to check that this element actually generates center. But it's a general fact that the center of group algebra is generated by finite conjugacy classes in the group, and then we just apply these to, and we just look for finite conjugacy classes, and these are precisely the classes of powers of B. Why I denote this element also as Z, because in the matrix presentation above, it goes to the diagonal matrix. So Z goes to this matrix, and it is also quite easy to check, but I will not waste time for it. We actually have have our algebra, which is a subalgebra of matrix algebra over its center. And actually, this is quite a huge class of algebras for which a good non-commutative algebraic geometry is established, and I'm going to talk about it later in the end of my talk. So and I also fixed the notation for Z. So let me write it down. We fix the notation for all the elements which were introduced for A, B, X, Y, and Z. I'm not sure if this really good notation, but it's enough for my talk. So, and what I'm going to tell today, first of all, I want to study irreducible representations of the group, and it turns out that it's really easy to classify all the irreducible representations. Then I proceed to Bannock representations, and I will say some general things about Bannock representations. And then finally, I introduce the notion of spectrum. And finally, in the end, I will tell about non-commutative functional calculus. Just NC functional calculus. So let us start with the irreducible representation, and I want to study by irreducible representations, I mean finite dimensional irreducible representations, but it turns out also that there are no unitary infinite dimensional representation, but we don't need this. So let V be irreducible module over our group. Let's say left module, and the dimension is finite. Dim V is finite. If the dimension is finite, then we have for every operator has an eigenvector. So there is some eigenvector, some non-zero eigenvector of B, such that B acts on V as multiplication by some complex number. And as B is the group element, it is necessary. It should be necessarily a non-zero number. So that means that in algebraic terms, that means that we have an inclusion of Z modulus. So inclusion of, so it's like the equivalent that we have an inclusion of one-dimensional.
Sorry, your B is actually X, is it?
B.
Do you mean involution or just another B?
No. B is not X. B is B is the generator of.
Oh, okay. So B is not an involution
of the Z.
Okay, thanks.
To remember it, AB is for representation as a semi-direct product, and XY is as for presentation as free product, and A is involution. So we have an inclusion of Z modulus. And that means that we have a map of induced representations. Should I recall the definition of induced representation? Or
yeah.
Okay.
Well,
so,
there's always some mixture between induced and co-induced, so please recall. Yes, please.
Okay. So I think here it is equivalent, but I will recall. So so the definition of induced representation, that induced representation from some subgroup from here is subgroup generated by B. So it's a Z generated by B to our group the infinity of some another of some representation X. X is Z module, is defined as X tensored over group algebra of Z on group algebra of the infty. So we construct representations of the whole group from the representations from the representation of subgroup. And in the theory of finite groups, this construction is crucial, but not only in the theory of finite groups, but particularly in the theory of finite groups, this this construction is crucial for construction of different irreducible representations. And here it is also the case, because, and the observation is that dimension of induced representation of induced representation equals dimension of the representations multiplied by the index of the group. So in our case, it's 2 by the index of subgroup. And here is 2. And it's I don't know if it is easy from this. No, I don't think it's like it's obvious. I don't think that it is obvious, but it is true. So thus, if we have an inclusion here, we have a map of induced representations. Yeah. So.
By the way, you meant by the modulus that 1 is acting by B, right?
By once again, please.
I mean, your Z module is what? It's B acting by operator B, right?
Yeah, by invertible operator on X.
Boris, I'm sorry, I have a question about this last formula. So is it correct that the group algebra of D infinity is a free module over C of Z?
Yes, it is true, and it's also a free model over its center.
So, if this is true, then this is the reason why the dimension of the induced module is twice the dimension of X.
Yeah. So yeah, as a right, as a module, then the group algebra of infinite diagonal group is generated over the subalgebra generated by B by 2 elements, precisely 1 and A. So as it is a free model, we are tensoring a free model with the finite dimensional vector space. So we should just multiply the dimensions.
Okay, thank you.
Yeah, and here it is also important that it is that the induced representation is an adjoint functor. So it's left adjoint to the forgetful functor, I think. Yeah, it is left adjoint to the forgetful functor. So if we have a map of like here we have a map from Z module to the infinity module. So that means by adjointness that we have a map from induced representation to V itself.
What does forgetful functor forget? It's just remembers
we have
how the subgroup acts and doesn't remember how the whole group acts.
Yeah, right. So we have a forgetful functor from the infty modulus to Z modulus, and it just forgets about the action of the whole group and remembers only the action of subgroup. And the induced representation functor is the opposite direction from Z modulus to the infty modulus. So and they are adjoint. So F is I think int. I don't remember. Then I think the notation is like this to F. So it's like, yeah, that means that if we have the map from Z module to the infinity module, then we have a map of induced module to the same D infinity module. So let me write it down. So we have an inclusion of Z modulus because we I recall because we have an we always have a one-dimensional submodule of an abelian group, and by adjointness we receive a map from induced representation from Z to the infinity of this one-dimensional module. I forgot to say that that what is C lambda? C lambda is a one-dimensional model where B acts by a character lambda. So B acts on some complex number C as lambda multiplied by C. And we have a map, and it's not necessarily an inclusion to V by adjointness of now there is a map of the infinity modulus. But we took V to be irreducible, so the image of this map should be a submodule of V, and as it is not zero because this was an inclusion, that must be the whole V. So this map is actually surjective. So it's actually so V is irreducible, so this map is surjective. And particularly this means that every irreducible representation of D infinity is quotient of induced representation, and that the dimension of irreducible representations are at most 2. So we proved the maybe it's lemma, but it's a part of a bigger theorem actually. So V is irreducible D infinity module, then it is a quotient of some induced representation from one-dimensional submodule, and dimension of V is at most 2. And so we can study closer those induced representations and to tell which of them are irreducible on or are, and which of them are not irreducible. And luckily, this induced representation can be described easily in the matrix form. I will introduce the notation. So the notation lambda b will denote this induced representation. So lambda is a character and b is like the generator of the group, but I think this notation is much easier to write and to remember. So it's the same as induced representation from d to infinity, from z to d infinity from this lambda. And in matrix form, this representation, so the dimension is 2, and in matrix form, we can easily describe lambda b. It is as follows. In lambda b, the action of elements is by in some basis can be described by these matrices. So A goes to this matrix, and B goes to diagonal matrix, but not scalar. Here is lambda, here is inverse of lambda. And I will not prove in details how this can be constructed, just an exercise, because it's like the standard machinery from theory of induced representations. We just have to compare everything. And from this matrix form, we can receive two useful useful properties of the representation. And so now it's the theorem, I think, because it describes fully the reducible representations of all of this group. So first of all, lambda b is isomorphic to some mu for another character b, if and only if lambda equals mu exponentiated to the power of plus or minus 1. So just comparing the eigenvalues of b, we see that we see that if two representations are isomorphic, it's either induced from lambda or from inverse lambda. And second, that lambda b is irreducible if and only if lambda does not equal plus minus 1. Because if lambda equals plus minus 1, then b is central, so we can change the basis to make a diagonal. So we so our induced representation splits into sum of two representations, yeah, so we have just proved this theorem. And now we are ready to define our non-commutative space definition by, but it just be a set for some time. So the infty with head, but without parentness. The entity with head, oh, I can't achieve good, nice head, is the set of finite dimensional irreducible representations of our group. And we will split this set into two parts, depending on the dimension of representation. And for I equals either 1 or 2, we also denote by with the index I, the empty head with index I, the set of representations with dimension I. Yes, so we split our set into two into two parts, and it's actually also a common thing in classical non-commutative geometry, if we can say like that. So I have first seen this trick in the, I think in the book of Fred van Oisten about non-commutative algebraic geometry, but this is also what one can do for spectrum of a C-star algebra. One can just the finite dimensional spectrum of C-star algebra. One can just consider all the dimensions not all together, but split. And the nice thing about it that all these parts are can be described as actually regular commutative algebraic varieties. So for the infty one, it is particularly easy because it has only 4 elements. So we have basically 4 characters for our group because we know its representation as a free product. So if he is a character, then y, then its value on x is ±1, and its value on y is ±1. So it's just 4 characters. And for the space for the set of 2-dimensional representation, everything is much more interesting. So for 2-dimensional representations, we use our theorem about how the irreducible representation of the maximum dimension look like. So we know that lambda b is irreducible if and only if lambda is not equals ±1, but also 2 of them are isomorphic if and only if lambda equals mu ±1. So that means that we should take the set of possible lambdas. It's is C with star, set of non-zero complex numbers. Then we must exclude the set of 1 and -1 from this set, and then we should factor this set by the action of the group with 2 elements. With the 2 elements, which acts as by inversion. So lambda is equivalent mu again, if and only if lambda equals mu plus minus 1. And from the, I think from the basic theory of symmetric polynomials, we conclude that this space is actually can be identified with C without 1 minus 1. I will explain how in a moment. So we actually have the space of two-dimensional representation, the set of two-dimensional representations in bijection with complex numbers without two 1 and -1. And how this bijection can be constructed. So I want the map from C without -1, 1 factored by Z by 2Z. I want a map to C without I can yeah, I want the map to C without 1 and -1. And this bijection is easy. It's if we think of this space, of the space of characters, it's just an evaluation of the character from the central element, but explicitly it is lambda goes to lambda plus lambda minus 1 factored by 2. And the inverse map is if we have some complex number C, then the inverse map from complex number C, we just take the roots of the particular polynomial. It's the I think this polynomial, but I'm not sure actually. One should check. Plus C plus 1 maybe. I think this. I think this polynomial, and it's the tricks from theory of symmetric polynomials, and the useful. It is very useful that we can also think about about elements of this space as central characters. So if we have if we have a representation of this form, then central element acts by this matrix. Z goes to lambda plus by scalar matrix with the same number, and so this makes also our set of irreducible representations of dimension 2, it shows us that it has a canonical structure of an algebraic variety. So here is a topology in it, and also some sheaf of functions on it, and to construct the topology, to construct some topology on the whole space, the infty had, we just need to glue these 4 characters to our space of 2-dimensional representations. So we need to glue the infty 1 to the infty 2. And there is actually several different topologies in algebraic geometry, in non-commutative algebraic geometry. One of the topologies, and the most used one, is called Fell topology. And it can also be constructed as several commutative spaces glued together. But in this particular example, we don't need some really hard theory. We just want to construct everything explicitly. So let us consider this space of characters, this set of 4 characters, and I want to introduce a notation for those characters. So notation, if P is equal P, if P and Q equals plus minus 1, then by he PQ, I will denote the character that acts on A as P and on B as Q. Yeah, and so let us construct. Let us glue now these 4 characters to our set of 2-dimensional representations. So we can draw a complex plane, yeah, and we have 2 points here. So we don't have 2 points here, so we have 1 and minus 1 excluded. And to glue our characters, we want to fit 4 points into 2 holes. So we should really make something non-separated, and to make those points doubled. And I will just tell some motivation for it a bit later, but I want to add these points as double points. So so how to say, we glue the character plus minus 1 1. We glue 2 characters as double point to 1. Yeah, so here is some double point. He 1 1 and he minus 1, 1. And here is a double point. He minus 1, 1, and he minus 1, minus 1. And also for symmetrically. And there is obviously some good explanation of this in terms of the felt topology I have just mentioned, and it but I will tell how to deduce this construction from the matrix presentation above. So we had a matrix presentation above. Let me recall it. I will do like this. So what if we somehow limit this representation to limit lambda to 1, for example? When we limit lambda to 1, we have b, the limit of b is this 1, 1. So, and a doesn't change. So lambda 1, so in this notation, if lambda equals 1, lambda b splits into 2 characters. He 1, 1, 1, and he minus 1, 1. And also if mu equals minus 1, then mu b splits into 1 minus 1 and minus 1 minus 1. That is some motivation for this topology, but I do not present that this topology is the best one can construct, because it turns out that it is impossible to construct a good sheaf of non-commutative functions with this topology. The sheaf I constructed, the presheaf that I constructed is not a sheaf, and the reason for that is that those double points have very different, very strange behavior when it goes to constructing some functions. But okay, so the infty is now has the infty has a topology of complex numbers with 2 double points. And actually, it's a structure of some of a non-separated algebraic variety, actually. And I don't use its structure of non-separated algebraic variety, but in more general results of Van Oisten, he obviously studies it as an algebraic variety. But he considers not this particular case, but more general algebras. Has a topology of C with 2 double points. With double points 1 minus 1. Yeah, so let us now proceed to Bannock representations, and we will study Bannock representations of this group. So let now X be a Bannock module. Let's denote it V again. It's not an irreducible. Let's V be a Bannock module. So we have a Bannock space with two independent involutions, two independent bounded involutions, and fortunately, involutions are those type of bounded operators for which we know everything. It's just a decomposition of the space into two subspaces, the positive part and the negative part. So that splits into here for us the free product presentation is useful. Splits into eigenspaces of X. And we will denote this like V plus X plus V minus X. And so when we have our Bannock space split into two parts, we can write our operators as matrices. So the matrix for X will be just 1 minus 1. It's better to write ID. It's better to write not 1, but actually ID V plus X and ID and minus ID V minus X. But I think that everyone will understand what I mean by 1 and minus 1. So just multiplication by 1 and minus 1. And Y has the form of matrix, but we don't know much about elements of this matrix, but we just denote them as follows: Y plus plus, Y plus minus, Y minus plus, and Y minus minus. The idea here that I plus minus acts from V plus to V minus. So to explain the notation, E plus minus X from V plus to V minus X. But we know that it is an involution, and as it is an involution, we have a condition for it to be an involution. So we want to write the condition that Y squared is 1 by some equation on the elements of the matrix, and the equations are as follows. So Y plus plus squared plus Y minus plus equals 1. Y plus minus Y plus 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 minus equals 0, and the same one the same but with inverse indexes. So plus oh no, here is a mistake. Here should be Y minus plus Y plus minus. Yeah, and two other. and two other are y minus plus, y minus minus plus. And the latest and those equations are very useful for us because of an important theorem. So as we can see from the matrix representation, these two operators are on the diagonal, so they act. They are actually operators on the single Bannock space. That means that we can compute the spectrum. Unfortunately, the spectrum of those two operators looks very alike. So the theorem about spectrum is that spectrum of an operator, so the operator y plus plus x from v plus to v plus, and y minus minus x from v minus to v minus. And the theorem is that spectrum of y plus plus without 1 minus 1 is the same as spectrum of y minus spectrum y minus minus without the same 1 minus 1. And this is for my talk, this is kind of fundamental result because the notion of spectrum goes from this theorem. So I think I don't have time to prove it. I just want to say more, and I won't prove it, but a remark for the proof for this theorem is we can observe from the second, let's observe the second equation and actually fourth, but they are symmetric, so I will consider on the second equation. Let me copy it. So it is useful for remark. If y plus minus is invertible, then the spectrums are equal actually. So because that means if it's invertible, we can rewrite this as a conjugation. Yeah. So y plus minus 1, y minus minus, y plus minus. And so the difference of the spectrum of these two operators somehow illustrate how these operators are far from invertibles. And that's really cool fact. And this observation helps us to define a spectrum of the representation. So let me proceed just to the definition. Spectrum of a representation. I'm being so spectrum of a representation is a subset of if where V is Bannock, again Bannock, the infty module, the infty module. I want to define a spectrum as a subset, as a certain subset of our non-commutative space, the infty. And the definition is here. So I also use this presentation of Y as a matrix, and here it is again. So it's matrix of Y, and here is interesting part. So we define the spectrum by parts again. First, I define the spectrum for considering only two-dimensional representations, and then I proceed to characters. So irreducible representation lambda b lies in spectrum in the in spectrum. Oh, yeah, lies in spectrum if and only if lambda b plus lambda minus lambda inverted b 2 lies in spectrum of the operator y plus plus. And the theorem on the previous slide gives us that it is equivalent. The equivalent statement is that minus lambda b plus minus of this element lies in spectrum of y minus minus. So two-dimensional representations are described as certain spectrum by the spectrum of these diagonal operators. And here everything is symmetric into y plus plus and y minus minus. But for characters, everything can be non-symmetric. So we defined when the so lambda is necessarily, it is irreducible, so lambda is necessarily not equal plus minus 1. And if we have a character, then we should consider those operators separately. So I will write one character, for example, and then I will say what to do with others. So, for example, he 1 1 lies in spectrum if and only if 1 is in spectrum of y plus plus. And generally, if we for other characters, if we change its so let me write for another character for 1 minus 1, so the same if and only if minus 1 lies in the spectrum of y plus plus. And what about minus 1, 1? It is in spectrum if and only if 1 lies in minus spectrum y minus minus. And the same, and if and he minus 1 lies in spectrum if and only if 1 is in spectrum of minus 1 is in spectrum of y minus minus. So, and so we observe here that that the characters in spectrum indicate the asymmetry between these two operators. Yeah, and those numbers was chosen in order for the spectrum of an irreducible representation to be itself to be this representation itself. So first property of the spectrum, actually, that spectrum of Bannock representation is quasi-compact. It is not compact because our space is not separated, but it is quasi-compact. And this is just because of spectrums of we can reduce our topology to spectrums of just y plus plus or y minus minus. And secondly, spectrum of irreducible representation equals this the class of this irreducible representation if V is irreducible. And that's how I have chosen numbers here. Third property, and it's partially property, partially a conjecture, because I think it can be more general, but I haven't proved it yet. So for polynomial in B, if f is a polynomial in B and B minus 1, then it is invertible. It acts by an invertible operator, but is invertible as an operator, is invertible in V, if and only if this polynomial is invertible in all the irreducible representations from the spectrum. And it's the property. This property is called spectral mapping theorem. And in this version, it is easy to prove, but I won't again because for the clear proof, one has to allocate more time. Is invertible in all irreducibles from spectrum. So as a corollary, the spectrum of such polynomial coincides with all the spectrums in irreducible representations. With yeah, so spectrum on V of this polynomial sigma v is just spectrum of the action of this polynomial is all the spectrums of this polynomial on axis from spectrum of v. And my conjecture is that it is also true for every element of the group algebra, and I've actually proved it for some other types of elements, but I was unable to prove it generally, and I think that I will do it someday, but unfortunately it's not yet. So yeah, and here are some of the properties. There are more of them actually, but those are the most cool ones. And it's like also the theorem. So I'll just say the sketch of proof of 3 and 4. So 4 is a corollary from 3, and 3 can be proved using the ordinary spectral mapping theorem combined with this fact only for B itself. So that is B is B is always invertible, but for the spectrum of B. So the linear polynomial in B is invertible if and only if, and invertible in every irreducible representation from the spectrum. And then we use spectral mapping theorem, and that's it. What we have not studied yet is the case when the spectrum is asymmetric in character. So, the question is when spectrums of y++ not equals spectrum or minus spectrum of y-. So we have, if we draw once again our non-commutative space with some double points, we have a spectrum like this, for example, only one double point present. And that is possible. It is a good, it is obviously possible because it is the situation of just the representation of character of one-dimensional irreducible representation, for example. But actually, it turns out that when the spectrum is asymmetric, then we can it turns out that we can easily describe the situation when the spectrum is asymmetric. And so again, the theorem, I will state this theorem for only one pair of characters for simplicity, but it can be translated to the second pair of characters. So suppose trivial character 1, 1, but here can be any other character. We don't use that this character is trivial and others are not. In spectrum of the representation, is a spectrum of representation V. And the symmetric character, the pair, his pair is not in the spectrum. and his pair can be written as -1, 1, is not in spectrum. Then the space V factors into the sum. V equals V say 1, 1 plus V 0, such that the infty acts on V11 just by character. So V11 such that V11 is actually a component of this character. So that means that the group acts on V11 by multiplication on this trivial character on 1. And spectrum and both he11 and he -11 are not in spectrum of spectrum of V0. So this whole asymmetry in spectrum fully describes by some factor of the representation where the group acts like by multiplication on a character. And so what we have here, when we have a symmetric spectrum, I will just say a few words on how this idea helps to construct the non-commutative functions, but I think I don't have time for this construction today. Maybe I will tell this some other day with something more, I don't know. But now I just want to say why this theorem is important and how it can help to construct non-commutative functions. So to construct non-commutative functions, I use the theorem of the result of Taylor that ordinary holomorphic functions have functional calculus in the neighborhood of spectrum, and I decided to take this theorem as a definition, as a definition of non-commutative functions. So we want to solve the inverse problem. We have some spectrum and we have some non-commutative algebra, and we have a set which we call a neighborhood of spectrum, and we want to construct some universal algebra, universal topological algebra that acts on this space. And here it can be done as follows. If the spectrum is not symmetric, so we have this situation. The spectrum is has only one character of the pair. We are using this theorem to split this representation into representation of character and the representation with now some symmetric spectrum. And then we use this knowledge to and when we have a symmetric spectrum, we have both double points in the spectrum. So it's more like this. We have, we may or may not have double points, but if we have one double point, we have a pair. And then we treat this space actually like the commutative space with and we are constructing the presheaf of functions of C itself, of C with some double points. And then we define a functional calculus separately on this factor and on this factor. And that's also why the resulting presheaf is not a sheaf, because it behaves rather strange in the neighborhood of the character. So I think I'm out of time, and I don't want to say. I have something. I have more to say, but I don't want to do it now because it will be too messy if I will be in a hurry. So I just want to end at this point and to answer your questions, and maybe sometime I will continue and tell more, but we'll see. So that's it. Thank you.
Okay, thank you very much. Questions, please, or comments?
A question about functional calculus. So, do you have some theorem or only some ideas for this?
I have a theorem, so I've constructed a presheaf, and these presheafs constructed in such way that it automatically acts on the space on this.
The presheafs on this spectrum.
The presheaf on this non-commutative space with double points.
But not a sheaf, only presheaf.
It's not a sheaf, but when we forget about double points and we shrink them into one, then it's a sheaf on the space of complex numbers.
So we're waiting for the second part.
Yeah, well, I want to say a bit more here. So that's where I wanted to use the matrix representation. So here is the matrix representation of the group as matrices with elements in polynomial ring. But we can instead change polynomial ring with the ring of holomorphic functions and consider matrices with elements as holomorphic functions, and actually that's how it is done. So, but I should obviously have more details. But if everyone is interested, I may share my text with someone, but it is very it is not quite it's on review by Alexey Yulievich, and it's quite in very pre-release version, and it can also contain a lot of mistakes and so on.
Okay, more questions, please.
Sorry, about your spectral mapping theorem. It's a single f function, is it? But it used to be basically sort of morphism. Could you extend by somehow morphism, replacing F by some morphism in your category? Or not just single F?
About here it is.
Yes, yes.
So the morphism and category. So
well, maybe done some sort of tuple. Could you generate, for example, get the two Fs or several Fs, which is again generating sort of module structure, the infinity, and then again use the spectral and try to get this spectral mapping theorem in this shape. It would be much better, right? But probably you don't have a concept of a morphism, is it? So
yeah, I think I don't have morphisms yet, but I also haven't thought about this because what category are you talking about? The category of the infinity modulus, or what category?
Yes, yeah, probably. But first you have to define this the algebraic geometry, right? You should have a sheaf, and the after have a morphism, and the after you can extend your spectral mapping theorems, I guess.
Mm-hmm.
But,
so I think I just haven't thought about it in this
I see.
in this setting.
But your presheaf locally, it looks like, do you have an idea what is that? So you don't have sort of localization, right? It's just, well, if you master sheaf generated by your presheaf, what is that? Is it?
The presheaf looks locally like in the general point, far from double points. It's look like just if we have a domain not containing double points, it looks like certain matrices with the elements in holomorphic functions in this domain. But if we proceed to the case of double points, there is actually a direct summand because we can act independently on this factor and on this factor. But I think I understand what I'm talking about, and also I think that this whole construction is really far from it just now. It's there are much more technical details to achieve before we can talk about this in some more general and even categorical setting, I think.
Oh, yes, sure, yes, thanks, I got it, yes. Okay.
Okay, more questions, please. Okay, if there are no more questions, then we thank the speaker. Thank you, Boria.